Integration by parts is a technique used to simplify integrals of the form the integral of f of x times g of x dx. Now, something I see often as an error is that students will think that the integral of f of x times g of x dx is equal to the integral of f of x dx times the integral of g of x dx, which this is definitely not true. And let's look at a very basic example to illustrate that this is not true. So if I wanted to integrate x squared dx, I know that this is equal to x cubed over 3 plus c. Now, what if I rewrote x squared as x times x dx? And if I thought that the above statement was true, then I could evaluate each of these things individually and multiply them together, which that would equal x squared over 2 times x squared over 2 plus c, and if I simplified that, that would equal x to the 4th over 4 plus c, and notice that these things are not equal to each other. So this illustrates that. So integration by parts is going to help us to figure out how do I integrate the product of two things. Integration by parts is useful when one of the functions f of x or g of x can be differentiated repeatedly and the other function can be integrated repeatedly without difficulty. The following are two such integrals. So I have the integral of x times cosine of x dx and the integral of x squared times e to the power of x dx. And in this first integral here, what I'm going to do is I'm going to kind of make two columns, and in the d column, d stands for differentiate and I stands for integrate. I'm going to place the x and the cosine of x in the other column. And so x is pretty easy to repeatedly differentiate because its derivative is 1, and then the derivative after that is 0. And cosine of x, if I were to integrate that, it has an integral of sine of x, or antiderivative of sine of x, and then the antiderivative of that would be negative cosine of x. Similarly, for this second integral here, if I make the same two columns, d and I can pretty easily repeatedly differentiate x squared. Its first derivative is 2x, then the next derivative would be 2, and then 0. And then the nice thing about e to the x is if I integrate, it gives me the same function over and over again. So this is kind of what we are looking for or hoping for when we're doing integration by parts to make our lives a little bit easier. So it turns out that integration by parts is an application of the product rule that we learn in differential calculus. So if f of x and g of x are differentiable functions of x, the product rule says that the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. And again, this is something you would have learned in differential calculus. So what I want to do now is I want to take the product rule, I want to take this equation, and I want to take the integral of both sides. And if I do that on the left-hand side, because the integral and the derivative are essentially inverses of each other, the left-hand side will go ahead and simplify to f of x times g of x. And then with the right-hand side, I know from integral properties that I can split this up into two different integrals. Now what I'd like to do is I would like to solve this equation for this integral here that I'm highlighting. So to do that, I'm going to isolate it by subtracting the other integral from both sides of the equation. So I'm going to take this thing and I'm going to copy it over. I have the integral of f of x times g prime of x dx is equal to, and then I have this thing, f of x times g of x, and I'm subtracting the other integral that was originally on the right-hand side of our equation. And so this essentially is the integration by parts formula, but this is not so easily digestible, and we want to kind of make it look a little bit more digestible. And the way that we're going to do that is we are going to say let u equal f of x and v equal g of x. And then if we do that, we get the following. So here's the integration by parts formula that is commonly used, and it's much simpler and more digestible in this form. We have the integral of u times dv is equal to u times v minus the integral of v du. And in college, I learned a very helpful mnemonic device to memorize this formula from a classmate of mine, and she would say ultraviolet super voodoo. And so ultra is the u, violet is the v, minus our integral sign looks like an elongated s, and then vu is v and du is du. So remember, all of the techniques that we talk about are supposed to make integrating easier. Even though this formula expresses one integral in terms of a second integral, the idea is that the second integral, the integral of v du, is easier to evaluate. The key to integration by parts is making the right choice for u and v. Sometimes we may need to try multiple options before we can apply the formula. Let's look at an example. This first example asks us to find the integral of x times cosine of x dx. So what I want to do is I want to make a choice for u, and in starting out in these more basic examples, what I recommend is trying to make u the thing that has a terminating derivative. In other words, when we differentiate it, eventually the derivative becomes 0. So in that case, or in this case, that would be x, because eventually if I repeatedly differentiate, it would approach, or it would become 0 at some point. And so if that's the case, this implies that du is equal to dx, and then we're going to make dv equal to whatever's remaining inside of our integral, which in this case is cosine of x dx. And essentially what we're doing to find v is we're integrating both sides of this particular equation, and the integral of dv is v, and then the integral of cosine of x dx would be sine of x. Okay, so I'm just going to copy down our formula really quickly using our mnemonic device. So we have ultraviolet minus super vu do. Okay, so using that formula, our original integral should equal u times v minus the integral of v du. So now I just need to go ahead and evaluate that integral at the end. So that is going to equal x times sine of x. And then the antiderivative of sine is negative cosine. And if I am subtracting off a negative, that becomes plus. And because this is a indefinite integral, we need to make sure we include our constant of integration. And so here is our final answer. Now remember, what we can do is we can check that this is the correct answer by taking the derivative. So I'm just going to say derivative check. And so this first thing, if I want to take the derivative of that, I need to use product rule. So I have first times the derivative of the second plus the second times the derivative of the first. And then now I need to take the derivative of cosine. That's minus sine, or negative sine of x. And then the derivative of a constant is 0. So what happens is these will subtract off to become 0. And then we're just left with x times cosine of x, which is the function that we were originally trying to integrate. So I'm just going to put a check mark to indicate that we did this correctly. Example 2 says find the area of the region bounded by the curve y equals x times e to the negative x and the x-axis from x equals 0 to x equals 4. What's nice here is that we have a picture already included. Here's our y-axis, here's our x-axis, and we are trying to find the area of this shaded red region here that's underneath our curve and bounded by the x-axis and the lines x equals 0 and x equals 4. So I'm going to call this area capital A. So we're trying to find capital A, and I'm going to say A is equal to, we can set up a definite integral to be able to find this, and that's going to be the integral from 0 to 4 of x times e to the negative x dx. And because I'm multiplying x times e to the negative x here, it's probably a good place to start to try and use integration by parts. So from earlier, I'm going to have u be the thing with the terminating derivative. And so du equals dx, and then dv is equal to e to the negative x dx. And I want to integrate both sides of that to get v. And if you use u substitution for e to the negative x, you'll get that the antiderivative or the integral of that is negative e to the negative x. So let's go ahead and start applying our formula, which again is ultraviolet super voodoo. And this example is a definite integral, so we have to be conscious of our limits of integration. So don't forget those. So you have the integral, we have a is equal to u times v, which in this case would be negative x times e to the negative x. And this thing, because this is a definite integral, we need to have our limits of integration here. And then minus the integral, and I'm going to copy down my original limits of integration again. And v is negative e to the negative x, so if I factored out that negative, then I'm going to change that to a plus sign. And then du is equal to dx. Now, I had a student in class ask me, why are we putting the original limits of integration here when previously we've put different limits of integration? That's because in this particular example, we're not using u substitution. So that's why we're putting the original limits of integration there. At this stage, if you wanted to, you could start evaluating this by plugging in 4 and 0. I'm going to save that, and I'm going to just copy down negative x e to the negative x. And then now what I'm doing is I'm taking the antiderivative of this thing. So I have minus e to the negative x. And again, if you want to, you can write out the u substitution that would land you there. And then now I'm evaluating this entire expression with my original limits of integration. And again, if you wanted to start evaluating this thing earlier, you can do that as well. I'm just kind of saving it and combining it all into one step here now. So now I can start to plug in my limits of integration. So let's do that. I went ahead and I expanded that a bit. And so if we combine like terms in this first set here, we get negative 5e to the negative 4th power, and then we have minus, this thing becomes 0, e to the 0 is 1, so we're subtracting off negative 1, which becomes plus 1. And so this represents the area of our shaded red region and our final answer.